Welcome to the course Business Analytics and Data Mining Modeling using R. So, in the previous lecture we started our discussion on neo-base and then we started our discussion on complete or exact base. We also understood the different steps that would be required if we do our modeling following complete or exact base. We also discussed few more points about class of interest and other things like limitation of complete or exact base. So, while discussing the limitation, we talked about that in complete or exact base sometimes it is difficult to if we have even if we have a small number of predictors, many new observations to be classified, they might not get exact matches. The values for those values of predictors being taken by those observations, those new observations which we want to classify. So, they might not get the exact matches in the data set, in the training data set. So, and also we talked about that if we include one or two more predictors having few categories, few classes, so how that decreases the probability of finding a match. So, because of these limitations, complete or exact base application of complete or exact base in typical data mining modeling exercises, that becomes difficult. So, what is the solution? So, that is the part that we are going to cover in this particular lecture. So, instead of complete or exact base, we can actually switch to what is called neo-base, the core discussion for this particular lecture, for this particular topic. So, therefore, we should switch to neo-base. So, we will talk about what happens in neo-base. So, in neo-base all the records are used instead of relying on just the matching records. So, as we talked about in the complete or exact base for a new observation that we want to classify. So, the values of different predictors that is being taken by that new observation, all those values have to be matched with the training partition records, and the matching records have to be identified. But as we talked about that sometimes that may not be possible. But in neo-base we do not actually just rely on the matching records, rather than the procedure or steps that we take, they incorporate the entire data set while performing Bayesian calculation, Bayesian probability values. So, that is of course with some relaxation, with some assumptions that we incorporate in neo-base. So, let us talk about the modification that we perform on complete or exact base to convert it into a neo-base scenario. So, let us discuss the neo-base modification. So, for example, if there are m classes of outcome variable, then let us take a particular class, for example, for class I of outcome variable. So, these are the steps that we are talking about, these steps for neo-base, and then we will analyze how they are different from complete or exact base. So, first step being that for class I of outcome variable there could be m classes. So, class I is one of those m classes. So, for class I of outcome variable we compute the probabilities P1, P2 and up to PP. That is for we have P predictors. So, therefore, we are computing P probabilities. So, we compute the probabilities of belonging to class I for each predictor's value. So, value could be x1, x2, xp. So, taken by the new observation to be classified. So, the values for the new observation, predictors values for the new observation. So, for each of those values we compute the probabilities of that particular record, and having that particular value for a particular predictor of belonging to class I. So, for class I we do compute these probability in the first step. So, for example, if there is a predictor x1, there is a predictor x1 and it has 3 classes, and one of those classes is actually the class of one of those classes is actually the value of new observation for that predictors. So, for that value we try to compute the probabilities of that new observation having that value, and the probabilities of belonging to class I with respect to that value. So, that would be the P1. Similarly, for the second predictor x2, it will also have some value if it being a categorical variable, as we talked about in the previous lecture, that all the variables are going to be whether outcome variable or the predictor variable, they are going to be the categorical variable. So, they will have many classes. So, therefore, for second predictor as well x2, there are going to be classes, different classes of this predictor, and one of those would be taken by this new observation, and for that particular value for new observation, we will try to find out the probability of that particular value belonging to class I. So, in this fashion, for each of the predictors values, each of the predictors values x1, x2 to xp, we will try to compute the probability of the these values belonging to class I. So, once this is done, once we have computed these values p1, p2 up to p for the pth predictor, then we multiply these values with each other. As you can see in this step, next step, compute p1 multiplied by p2 and up to the multiplication goes up to a pp, and then we multiply it with the proportion of records that are belonging to this class I. So, out of all the records that we might have, how many records out of the total records actually belong to class I. So, that proportion we will multiply using we will multiply that proportion into this particular value, right. So, we will have to compute p1 into p2 into multiply up to pp, and then the proportion p of ci, probability of ci. So, now these two steps as expressed in the third step. So, these two steps have to be repeated for all the classes. So, we talked about for a specific class I, but these steps, so there could be m classes in a outcome variable. So, the m classes for each of those classes c1 to c2 to c3 up to cm, for each of those classes we will have to do this exercise step 1 and step 2. For each of these steps we will have to compute and finally arrive at the values that we have in the step number 2 for all the classes. Once this is done, once we have done these computations for all the classes with respect to the new observations values, then we come to the next step. Now, to compute the probability of the new observation belonging to class I, divide the value computed in step 2, right. So, all those probabilities multiplied by the proportion for that class. So, we divide that value by the summation of values computed in step 2 for all the classes. So, we talked about in this step 3 that this step 1 and 2 have to be repeated for all the classes. So, the values that we get for different classes, we will have to sum those values, and this value will become the denominator, and will divide the value computed in step 2 for class I with this summed up value. So, that will give us the probability of new observation belonging to class I. Now, in the next step we will execute what we have done for class I for the remaining classes of the outcome variable. So, for all other classes also we will have to perform this. So, from this you would see we will have to do lots of probability computation. We'll have to compute lots of probabilities and then followed by other multiplication or division operations, and that has to be done for all the classes. So, for all the classes, once we execute this, then we will have the probability values of the new observation belonging to each class of the outcome variable. So, if there are m classes, in the outcome variable, if our outcome variable is having m classes, C1 to C2 to Cm. So, once we have executed the probability value for that new observation P1, P2 for all these classes. So, once we have reached this step, then we are going to classify the new observation to the class with the highest probability values. So, among these values that we have computed following 4 or 5 steps, right, then we will find out the highest value, and the class of that highest probability value, that would be assigned to the new observation. So, new observation would be classified to that particular class. So, you can see most probable class method that is being applied. So, class having the highest probability, that would be assigned. So, let us recap some of these steps. So, what happens in naive Bayes modification which is slightly different. Some calculations are different from complete or exact Bayes, which we will discuss later on. So, in the first step, we compute the probabilities of belonging to class I for each predictor's value taken by the new observation to be classified. Right. So, as we discussed, for each of those values x1, x2, we try to find out the probabilities. We try to compute the probabilities of those values belonging to class I. So, then we compute this expression of all these probabilities multiplied by the proportion for that class, and then this is executed for all this step. Once we have the values for all these classes, for each of those class, the value for that class, and it would be divided by the sum of all those numbers, and that is how we will get the probability for all the classes. So, let us look at the naive Bayes formula. So, this is the formula. We are going to compare how this is different from the complete or exact Bayes formula that we saw in the previous lecture. So, you can see PCI, probability of a observation belonging to class Ci, given the predictors values that are x1, x2 and up to xp. So, p predictors are there for each of the predictors, then observation is going to have some value. So, given those values, what is the probability of that observation belonging to class I. So, this can be computed using this particular expression, right. So, here you can see that probability of the observation belonging to x1 given this particular class Ci, then probability of this predictor value x2 belonging to probability of this particular x2 given the class Ci, then the conditional probability of xp with respect to Ci. So, all these numbers have been multiplied, then the proportion is also multiplied, proportion of records that belong to this particular class Ci, that is also multiplied. Then in the denominator you can see the same expression is there for all the classes. The first expression is for C1, then it is going to be followed by the same expression, similar expression is going to be for the C2, and similarly for other classes up to the last class, that is the mth class. So, you can see the same is here. Now, let us have a look at the let us have a look at the formula for complete or exact Bayes. So, this was the formula for the complete or exact Bayes. So, you can see here. So this is the conditional probability expression that we generally use. So you can see probability of a particular observation belonging to Ci given the predictor's values, and this is how it is expressed, right. So you can see one difference, that is in the numerator as well as in the denominator, the different expression that we have. This particular value, this particular expression, this particular value, probability of different predictors values, right. Probability of a particular observation having these predictors values and given the class Ci. So this particular expression has been changed to this multiplied product of different probabilities, right. So this is what is explained in the few more points. So Naive Bayes formula is directly derived from the exact Bayes formula after making following assumption. So what is that assumption? That predictors values x1, x2, xp occur independent of each other for a given class. So this is the approximation that we have done. P x1, x2, xp, this was the probability that we were supposed to compute in the complete or exact Bayes, and now this is the product of probabilities that we are now computing under Naive Bayes, right. So you can see for each of the observation, once we say that these values occur independent of each other, so this particular expression can be written in this form, where as you might have studied in your probability courses, that if the events occur independently, then the probability of those events happening is going to be the product of the independent product of the probabilities of the independent events. So this is the same thing that we have done, because these value can occur independent of each other, that is the assumption. So this particular expression can be decomposed into this form. So from the conditional probability we have reached to the, in a way, unconditional probabilities with respect to unconditional, in the sense that the vectors values are going to be independent of each other. So this is the approximation that has been done. However, this particular assumption might not sometimes it might not be true in practical situation, but however, what has been seen that the results that we get by applying Naive Bayes are quite good in comparison to other techniques, despite some of the times when this assumption is not met. So let's move forward. So as we discussed that for classification, Naive Bayes formula works quite well. Now since another important aspect is, since we don't require probabilities values to be accurate in absolute term, rather just a reasonably accurate rank ordering of these values. So essentially, as we discussed here, that once we compute the probability values, right, then we need to find out the highest value, and the particular new observation is going to be assigned to that class belonging to that highest probability value. So therefore we just need to find out which probability value is higher, which are lower. In a sense, we need to just have the rank ordering of these probabilities value. So even if some of these probabilities values are not accurate, why we are talking about this? Because we have made one assumption in Naive Bayes. We have converted the conditional probability into the product of unconditional probabilities for the predictors values, right. So because of that approximation, because of that assumptions that those predictors values are going to be independent of each other, so our probabilities value are not going to be accurate more often than not, but that is not going to create any problem for our modeling exercise. Reason being that we just need to find out the order of those values. We need to just know the rank ordering, and that rank ordering is going to help us in finding the highest rank, and therefore the class, the new observation, is going to be assigned to the class of the highest probability value. So, we just need to have the rank ordering, and that is why when we were saying that in even if that assumption of independent predictor values is not met, in practice the Naïve based model works quite well. Reason being that we just need accuracy in rank ordering and not in the actual probabilities values. So, for the same reason that we have been discussing, we should use the numerator only, so and drop the denominator, which is common for all the classes. So, let us go back to the formula that we discussed. So, this is the Naïve based formula. So, if we are just arranging the rank ordering of different probabilities values for different classes, so you can see the numerator this as per this expression, the Naïve based formula, the denominator is going to be the same for all the classes, because it is the summation of probabilities value computed for all the classes. So, this is going to be the same. So, therefore, for the comparison of probabilities value to create the rank ordering, this is not going to matter. So, we can just focus on the numerator and compare the numerator values, and still will end up with the same rank ordering. So, that is another simplification in Naïve based that can be performed. So, we will not have to compute all the values, some of the calculation we will not have to perform, which are related to denominator, and we can just focus on the numerator and the computation that are required for the same. Now, till now what we have been discussing is mainly when we try to minimize the overall classification error, or try to maximize the overall classification accuracy. So, as we have been discussing for other techniques, multiple linear regression or K-NN, specifically K-NN, because there we discussed mainly about the classification task. So, when we have a class of interest, right, so how our steps are actually going to change. So, the earlier steps were actually the typical scenario, which is that we are looking to minimize the overall error. So, when we have a class of interest, so we want to identify more records belonging to the class of interest, even if it comes at the expense of misidentifying or misclassifying some of the records belonging to other classes, right, because the focus is on one particular class of interest. For example, the financial reporting example that we discussed in the previous lecture of Naïve based, we talked about that an auditor, an accounting firm, would be interested in finding the financial reports which might be fraudulent, and not in the reports, the auditor or the firm might not be interested in identifying the truthful reports, because they would like to do a more serious scrutiny of the financial reports which might be fraudulent. So, therefore, they would like to identify more of those reports which could be the candidate for serious scrutiny, which could be the fraudulent reports, and therefore, it would be important for them to identify those reports, those statements which could be fraudulent, even if it comes at the expense of misclassifying some of the truthful reports as fraudulent reports. So, let us discuss steps when we have a class of interest. So, first step is typically going to be specifying a cutoff value for the class of interest. So, this cutoff value, as we have been talking about in the previous lectures as well, that this cutoff value when we have a specific class of interest, so the cutoff value, the default cutoff value is typically 0.5, when we have a class of interest, so we are interested in identifying more of a particular class members, and other classes that could be there, we are not too much focused on them. So therefore we would like to identify more records of this class as we have discussed. So this particular cutoff value can be treated as a parameter of the model. This can be treated as the parameter of the model or slider, right. So we can slide this value, this cutoff value. So it can sometimes be 0.2, it can sometimes be 0.4. The main idea is to identify more of class 1 records, right. So if there are many classes, of course the probability of a record belonging to class 1, that is class of interest, is going to be slightly on the lower side. So if we change our cutoff value that we are supposed to specify to, let's say, 0.2, so any value that any estimated probability value for a particular new observation, if it is it is more than 0.2, then that particular record is going to be classified as belonging to class of interest, that is C1. Otherwise not, that means it would be belonging to one of the other classes, right. So this is the typical idea. So we would like to specify a cutoff value which can help us in identifying more of the records belonging to class 1. So once we do our modeling exercise, once we have estimated the probabilities values for different observations, right. So once for different observations, once we have the probabilities value of belonging to class 1, right. So we can always slide the cutoff value, and in that fashion our results for the classification matrix, they will change as we slide the cutoff value, and therefore we can find the appropriate cutoff value which can help us in identifying more of class 1 records, more of class of interest records. So as a first step we have to specify user specified cutoff value. So one of when we discussed the performance, when we were discussing performance metrics, then also we had done one particular exercise using Excel, where we were actually changing the cutoff value, and we had saw that the results in the classification matrix they were also changing. So that is the particular exercise I am referring to. So that kind of exercise can help you in finding. We also created a one-way variable table to have different cutoff values and the respective the classification error numbers and accuracy number. So that kind of exercise can help us in specifying, in establishing a cutoff value for the class of interest. So once this is done, we move to step number 2. So this is quite similar to the regular scenario step. So we compute the probabilities P1 to Pp of belonging to class of interest for each predictor's value that could be x1 to x2 to up to xp, taken by the new observation to be classified. So as discussed in the regular scenario, the new observation will have some values for different predictors. So they could be x1, x2, xp. So for each predictor the value could be some class. So for that particular class we have to find out the probability of that class belonging to class of interest. So once these probabilities are computed, then we can move to the next step where we multiply all these probabilities P1 to P2 to Pp. So that is with respect to each of the predictors value for the new observation, and then we multiply it by the proportion of the records belonging to class of interest. So that is nothing but the probability of a record belonging to class of interest. So once this is done, so we will have this particular value for the class of interest. Now we will have to execute these two steps for all the classes, right. So especially this is required if we want to compute the if we are not just focusing on the numerator and we want to compute the value, the Naïve Bayes value for the probabilities. So in that case, the step number 3 would be required for all the classes. And even if we are not using the denominator, even then for the comparison purpose, we would be we would be required to compute these values, especially in the regular scenario, not so much in the class of interest. So let's move to the next step, that is to compute the probability of the new observation belonging to class of interest. We divide the value computed in step 2 by the summation of values computed in step 2 for all the classes, right. So in this step 3 we said about computing the step 2 value for all the classes. Now all those values would be summed up, and then that would be used as the denominator to divide the value computed in step 2 for the class of observation. So that will give us the probability of new observation belonging to class I. So in this particular, as I clarified, that we have both the numerator and denominator and not just the numerator. So once this is done, we can classify the new observation to the class of interest if computed probability value is greater than the cutoff value defined in step 1. So once this probability value is known, as we discussed there, that for example, if the value is if the value comes out to be 0.25 and the cutoff value is 0.2, then probably that particular new observation is going to be classified to the class of interest. So with this we will stop here, and in the next lecture we will learn Naïve Bayes modeling through an exercise in Excel, and also we will try to do an exercise in R. Thank you.